Hello, this is section 3.4 for Calc AB, and today we'll be talking about concavity and the second derivative test, which is a very nice alternative to the first derivative test. But I'll warn you, the first derivative test always works. The second derivative test most of the time will work, but that's the benefit to the first derivative test. Okay, so first and foremost, definition of concavity. So if your function's differentiable on an open interval, I, the graph is concave up when the derivative is increasing on that interval. And the function is concave down when the function or the derivative is decreasing on the interval. So here's where it can start to get a little confusing because where the derivative is positive, your function's increasing. Where the derivative is increasing, the function's concave up, so it starts to get a little jumbled up. So you might want to make some flashcards to help you keep these straight, but you can always sketch it out to help you. So here's our original function, where you can see it's concave up, no question. And if you were to sketch the derivative, notice the slopes are negative. Then we have the horizontal tangent line, so we have 0, and then the slopes are positive. So I just kind of sketched a derivative, and notice the derivative is increasing where your function is concave up. Oh, isn't that cool? And then over here where the function's concave down, so you have your slopes of your tangent lines are positive, and then until you reach the point where you have a horizontal tangent, and then here your slopes are negative. And notice where your derivative is decreasing, your original function's concave down. So make some flashcards to help you keep those relationships straight. Okay, so given the graph of the function, discuss the concavity in comparison to the derivative. All right, so this is our original function here. And already you can tell we start off concave down, and then we switch to concave up. So I went ahead and sketched the derivative. So our slope is 0 at these 2 points. So I plotted those zeros, and we're increasing, so we're above. Decreasing, slopes are negative below, and then increasing, slopes are above. And you can see where your derivative is decreasing lines up perfectly with where your original function is concave down. Where your derivative is increasing lines up with where your original function is concave up. Okay, so now test for concavity, we'll want to use the double derivative. Okay. So, and coming back up here, if I was to sketch the double, so if I was to sketch the derivative of the derivative, it's getting the double derivative. Notice the slope of the tangent line is 0 here, so it'd cross. We're negative, all our slopes are negative, so we'd be down here, and then all of our slopes are positive, so we'd be up. So can you kind of imagine that the double derivative would be a line, roughly? And notice where the double derivative is negative, lines up with where the function is concave down. Where the double derivative would be positive is where the original function is concave up, and that's what this is talking about here. So where the double derivative is positive in the interval, the graph of the function is concave up. Where the double derivative is negative is for all x in the interval, and when the graph of f is concave down. Sorry, I kind of tried to sketch it. If we were in the classroom, I'd put that on the dry erase board and we'd give you a little bit better representation. All right, so locate guidelines for concavity. Locate the x values for which the double derivative equals 0 or the double derivative is undefined. Realize asymptotes are where you could easily change concavity, so you'll have to be careful. Use these x values to determine the test intervals and then test the double derivative. So just like we were using the first derivative number line to test for increasing and decreasing, we're going to use the second derivative number line to test for concavity. Right? So that's exactly what we do. So we find the first and the second derivative, then we set the second derivative equal to 0. Now, always, just like with critical numbers, the critical numbers have a special name. Remember, critical numbers are your potential relative extrema, and they're called critical numbers. Well, where the double derivative equals 0, it doesn't have a special name like critical numbers. So I just call them potential inflection points. But just like those critical numbers were potential relative extrema, this is a potential inflection point. So you're not guaranteed that you change concavity at 0. Just like with critical numbers, you weren't guaranteed you were going to get a relative max or a relative min. So then we take this up here and we create our double derivative number line, put your potential inflection point on there, and then check the intervals in the double derivative. Where the double derivative is negative, your original function is concave down. Where your double derivative is positive, your original function is concave up. And there you go. Right? Now, points of inflection are where you change concavity. So there's 3 different types, and this is my way of describing them. This isn't anything formal. I called this type a horizontal inflection point because the slope, your tangent line there is horizontal. This I call a smooth inflection point because it's just going to gradually happen. And notice the slope of the tangent line has a slope to it. And then I called this one a vertical inflection point. But again, those are Mrs. Cogswell's descriptive terms. That's not, they don't really have any formal names. The inflection points kind of get the shaft because all of your relative max, relative min, you can visually see what that looks like. Inflection points, we just say all 3 of these are inflection points. They don't get a special name attached to them. Okay, so I kind of give them descriptive names. So horizontal inflection, smooth inflection, vertical inflection points. Okay, but the key thing is, with all 3 of these, the concavity changes. That's the key. Okay. All right, and then your tangent lines are going to be going through your graph at these inflection points. See, that's what this is saying. All right, so points of inflection on a graph where the double derivative equals 0 or the double derivative might not be defined, and that's where you might have a vertical inflection point. But where the double derivative equals 0, it could be a smooth or it could be a horizontal. Okay. All right, so here's an example of determine the inflection points and discuss the concavity for this function. All right, so when you see concavity and inflection points in your brain, you need to think, I need the double derivative. So that's the first thing you're going to do. Do the first derivative, then the second derivative. Set your second derivative equal to 0. And you actually get x equals -1 and 2. Those are your potential inflection points. Put those on the second derivative number line and test these intervals in the second derivative to see when it's positive and negative. If the second derivative is positive, you know that the original function's concave up. If the second derivative is negative, the original function's concave down. Because we changed signs, we have an inflection point at -1. Because we changed signs at 2, we go from concave down to concave up, we have an inflection point at 2. Right? And that's what I put over here. Now, because we don't have special names for inflection points, you'll notice that I just said the double derivative G changes signs at -1 and 2. Notice I don't have to say from positive to negative to justify a relative max. So that's kind of nice. Okay, and then also one more other thing. Notice that I plugged these x values back into the original function to give the ordered pairs. Okay. All right, and then here's another example of determining concavity, and here's where I want to point out that with this rational function, you have 2 asymptotes at +1 and -1. You can change concavity when you cross over the asymptote. So you do need to still put those on your number line, just like we did with increasing and decreasing. If there's an asymptote, you still want to put it on the number line. Just write undefined above. And yes, you can still change concavity, but they're not inflection points. Okay. So I did the double derivative. Here's the first, here's the second, set it equal to 0. All I didn't get anything out of the numerator, and all I got were the asymptotes from the denominator that aren't even defined. But I still put those asymptotes on the double derivative number line to test. Okay. All right, now last, second derivative test, which is really important. This is another way of determining relative max and mins. using concavity. And I said earlier, this does not always work, but it's a really nice test if it's convenient and if it works, of course. So what it's saying is if the double derivative is positive where you have a critical number, so if the double derivative is positive, it must be concave up. And if it's concave up, then at that critical number, it must be a relative min. Oh, makes sense. So then the next, if the double derivative is negative, meaning concave down, you must have a relative max at that critical number. Okay, so it's using concavity to justify your relative extrema. Now, here's the problem though. If the double derivative equals 0, the test fails. Darn. Okay, and then you have to go back and use the first derivative test. So that's why the first derivative test will always work. And the double derivative test is nice when it does work. Okay, so here's an example. Use the first and second derivative tests to find the relative max and min points of the function. Okay, so we're going to do both tests and you'll see we get the same answer. Now, the nice thing is both of these always start off the same. You find the derivative, set it equal to 0. You have to know where your critical numbers are. So that's what I did first, and it's at 2. Okay, so first derivative test, we make a first derivative number line, test your intervals in the derivative to see where your function changes from increasing to decreasing or vice versa. And in your derivative, you get a negative and a positive, so it's a relative min. And here's the justification. Now the second derivative test, after you get the critical number, do the second derivative, and notice you get 2. That means that if the double derivative is 2 and it's positive, this function is always concave up. And if the double derivative at 2 is positive, and I wrote over here the function's concave up, you must have a relative min. So here's the justification. Because the double derivative at 2 is positive, f of 2 equals negative 2 is a relative min. I would almost add in there that the derivative at 2 equals 0 and this. I think that'd be a better way to word that. So I put a note to yourself in your notes, and I'll say this in class. I would almost prefer you've identified that over here, but I would almost put that in your reasoning too. That because we know f prime of 2 equals 0, meaning you know it's a critical number, and the double derivative at 2 is greater than 0, then this must be a relative min. But it's using the concavity, the fact that it's concave up. All right, here's another one. Use the second derivative test to find the relative max and min points of the function. Okay, so first derivative, set it equal to 0 to get your critical numbers. First step. Then find the second derivative and plug your critical numbers into your second derivative. Now, immediately when you plug 0 and you get 0, it's like, ah, crap. That means inconclusive. You got to go back and use the first derivative test. So that's what I've done over here is I created a number line, put the critical numbers, and I just have to test around 0. And I notice, oh yeah, you actually do have a relative max there. But when you plug 1 into your double derivative, you get a positive number, meaning you're concave up. And if it's concave up, it must be a relative min. Okay, so you notice in my justification, I said the derivative changes from positive to negative at x equals 0, meaning f of 0 equals 0 is a relative max. So that's the first derivative test I had to use. And then here, because the double derivative at 1 is greater than 0, f of 1 equals negative 1 is a relative min. All right? So that's the second derivative, what you have to put for your justification for the second derivative test. Okay, now this last page just has some additional examples that has some slightly interesting problems because you've got some issues with, remember when you pull critical numbers out of the denominator, you have to be a little bit more careful. And here we ended up throwing something out because it wasn't even in the domain of the function. So, but it says you do your concave up, concave down, and inflection points, and then here's the second derivative test for your relative extrema. So these are two really good examples where they have, and here's a trig example. So go through, look through those examples, and we'll definitely do these in class, but write these out. And if I write something down and you don't understand why I put something, email me and I will happily explain it to you. So Okay, make sure you do your homework on this and let me know if you have any questions.